The focus of this video, and indeed most of this week, is going to be on estimation. There are two basic paradigms in which estimation can occur, one of which, the frequentist approach, is your traditional statistics textbook approach to probability and to estimation. The second is the Bayesian method, the Bayesian approach, which we talked about Bayes' rule a couple of weeks ago, will be more recent development, so to speak, in the statistical community. We'll talk about how these two approaches differ and how we will utilize them in the weeks to come. Most of the remainder of this course will focus on a frequentist approach to estimation, whereas some of your future courses will kind of start to sprinkle in some of the Bayesian aspects. In the frequentist framework, it's basically our empirical probability approach. We are assuming that the true probability of an event is the relative likelihood of observing an outcome in experiment multiple times. In other words, if we were to say I want to know the probability of success in this endeavor, I could simulate it or reproduce it many times and look at the proportion of successes to the total number of attempts. That proportion of successes, this empirical proportion, is expected to be the true probability, singular probability of an event occurring. Recall that the probability in distributions are functions of parameters, so we might be more interested in characterizing the distribution. So how do we characterize the distribution? We have to figure out what parameter values are most consistent with our data. The parameters of the distributions and the probability themselves in the frequentist framework are fixed, unknown numbers. And we have to use data to estimate them. Now, it's a really important point that we think about this, that the parameters themselves are unknown. We don't know going into it what the value is. But in the frequentist framework, we make a very large assumption that there is a true value. If I'm looking at a binomial distribution, say I'm flipping a coin, and I want to know the probability of getting ahead, the frequentist approach will say there is one true probability of getting ahead for that coin, and it does not ever change. We simply are flipping it many times and seeing different realizations of the random variable. But the true probability, the true proportion, the probability of heads is constant. And that's a very large assumption, or a very large part of the frequentist framework. Our goal in a frequentist framework is to then figure out, well, if that coin has a singular probability of a head, I want to estimate it. I want to figure it out. In real life, we'd say, well, we're going to assume this coin is fair, 50-50. Well, what if I don't want to make that assumption? What if I'm looking for the probability an ad is successful in inducing a purchase? In that case, I don't know what the probability, what is the likelihood this ad is successful? I don't know, but I can collect data and use that data to estimate the parameter of which a frequentist would say it is a true singular number, and I'm going to try to estimate it. Bayesians, on the other hand, basically look at probability as from a little bit of a different perspective. They don't necessarily think that there's one number. They say, instead of saying that there's a fixed true probability, probability is simply our degree of belief in something. We might not be able to repeat this experiment thousands of times. So if I can't repeat it thousands of times, how can I figure out the probability? Well, what I'm going to do is I'm going to say the probability of occurrence is how much I believe it's going to occur. Now I'm going to use the data that I collect to update my degree of belief. In other words, I might say, I think that this coin is fair, 50-50. Then I flip it 50 times and I get 49 heads. Well, that's going to update the degree of belief. I probably don't believe the coin is fair anymore. I'm using data to update my prior beliefs. Remember when we discussed Bayes' rule, we talked about a prior probability. Then we collected data, and we updated our prior to form a posterior belief in the probability of occurrence. The parameters in the model are no longer fixed. There is not one and only one true probability in the Bayesian methodology. In the Bayesian methodology, the parameters themselves follow distributions. So the probability of flipping a head in a single coin flip has probability P. And I would say a Bayesian would say, well, there's not one true P. P follows a distribution, perhaps like a uniform distribution between 0 and 1. That might be my initial belief. Then I collect data. Well, where do I think P is now? Remember I told you I assumed that the coin could be anything. Then I flipped it a bunch and I got 49 out of 50 heads. Well, that updated my initial belief to say, well, it's probably going to be about 90% heads. But maybe I'd say between 90 and 100%, or not 100%, 90, 95%, because it would give me a range. Why would I say a range? The true probability, follows a distribution. We have uncertainty in the value of the parameter, and there is not one true value. The data firms up or dispels our prior belief in the parameter. In this course, we're going to focus on a frequentist approach, but we will see the Bayesian framework appear in many future courses, especially in an entire course that's focused only on Bayesian statistics.